So, hi everyone, I'm Dana. I'm a PhD student in auditory neuroscience here at Harvard, and I actually got into the field and got interested in sound because I've been a musician for most of my life. So I'm going to give you a quick whirlwind tour, a taste test of what I think is the very fascinating field of the neuroscience of music perception. So music has been around for a really long time. Archaeologists have found remnants of bone flutes, like those shown here, that are over 40,000 years old. And humans have been singing for even longer than that, but this doesn't leave any sort of archaeological evidence. So the basic thought is that as long as we've been human, we've been making music of some kind. And music is seemingly universal. It's been found in every culture, both throughout history and also in the current day. And it's used in a whole variety of different cultural events, including weddings and funerals, sporting events, dances, as well as solitary listening, which is how we probably spend most of our time interacting with music these days. And we tend to really love music and seek it out. So raise your hand if you currently play or have ever played an instrument. Pretty much everyone. Okay. Raise your hand if you have already listened to music today. All right, cool. Raise your hand if you still remember the lyrics to your favorite songs from middle school. Yeah. And raise your hand if you've ever gotten chills while listening to music, or if you've ever been brought to tears. Yeah, so that's pretty crazy, right? Music can make people feel happy and sad, and because of that, it's become a huge part of kind of marketing and advertising these days. And humans spend billions of dollars every year on acquiring music and listening to music. So today, I just want to kind of pick your brain and ask you to consider why we do this. Music is just sound, it's just vibrations that travel through the air and hit our eardrums. So why do we spend so much time and money seeking out this particular type of sound? And why do we imbue it with such emotion and meaning? So this question is actually really difficult to answer because unlike other sort of perhaps unique to humans systems like language or theory of mind and social interaction, there's no clear evolutionary advantage for music. This is a huge debate. And it's hard to sort of get at that because we can't really use our traditional evolutionary biology techniques in order to get at music. So instead we have to do experiments to kind of try to answer this question in a variety of different ways. So today I'm going to be musing about the kind of nature versus nurture debate in music, whether music has a biological or a genetic basis. And one way that we can look at this is to see what aspects of music and music perception we might share with other species. We can also look at what musical abilities we might have built into our brains and our perceptual systems by looking at what we can do at birth and in early development. And we can also get an idea of the biological nature of music by looking at music across different cultures who might have very different musical systems. And another interesting way to try to figure out the role of music in our lives, and as a neuroscientist, my favorite way, is to look at music in the brain and how the brain processes and understands music. And so we can try to ask the question of whether there is a part of the brain that specifically is involved in music perception. So in general, the way the brain is organized is we tend to have certain brain regions that do really important things, like face perception, or emotion, or thinking about other people's thoughts. And so it's not crazy to ask whether we might have a music region, since music plays such a big role in our lives. And there's also a question of whether music is really its own sort of thing, or whether music kind of piggybacks on brain areas and perceptual abilities that we might use for other things, like for understanding speech and language, or math, or a variety of other sorts of things. All right, so let's start by looking at our animal relatives. So first of all, do animals even have music? Of course, this all depends on the definition of music that you want to use, but I'm going to say today that a lot of the sounds that we consider musical that other animals make, like birdsong or whale song, that they sound musical to us, but not necessarily musical to the animals. And this, again, depends on the definition, but in general, a lot of the ways that people define music involves some aspect of enjoyment. So we produce music and we consume music just because we like it, not because it serves some sort of absolutely necessary goal. Whereas in animals, Their song tends to be used for communication about predators or for courtship. There isn't a lot of evidence that any animals produce sound just because they like it. And so even if animals don't have a complex system of music the way we do, they might share some sort of music perception abilities with us. And surprisingly, this doesn't seem to be true, even for some of the most basic sort of musical things that we can do. So one example of this is our ability to use relative pitch. So relative pitch is our ability to understand that a melody can be the same melody regardless of which note it starts on. So if I sing the song Happy Birthday, it's still the same song whether I start down here or whether I start up here. As long as it follows the same pattern, we will all recognize it as Happy Birthday. It seems totally trivial to even have to explain that. But surprisingly, animals can't seem to do this. So a lot of research has been done with starlings, the songbird shown here, and with a lot of practice, they can actually teach starlings to be able to discriminate between melodies that are simply ascending versus descending tone sequences. And they can do this well after enough training and reward, and once they can sort of do this task, they then test them by taking the same melodies and shifting them up in pitch, but the birds can no longer do the task. They treat them as if there's entirely different melodies and entirely different tasks, and you have to retrain them completely to discriminate these same melodies, which we would have absolutely no problem with. Another sort of basic musical requirement in order to perceive music is our ability to extract a beat. So this is, you hear a song and you can tap your foot or kind of clap your hands along with the beat. It's pretty easy, even for some pretty complicated rhythms, people usually settle on the same sort of beat. But that kind of belies how really complex that actually is, to be able to abstract a beat away from the sound. And there's actually not a lot of evidence that animals can really do this. There's a lot of really great YouTube videos where animals have been trained, seals and birds and monkeys, to tap along with a beat or to bob their heads. But pretty much always, they aren't really able to anticipate the beat. Instead, they're kind of reacting every time they hear a beat, and so they're always just a little bit behind. Whereas humans were able to kind of predict when the beat's going to happen and actually kind of tap our feet or clap sort of actually a little bit ahead of the beat. And even animals who, there's a few examples, also on YouTube, of animals who have been found to actually be pretty good at this. One of them is Snowball, this cockatoo bird right here. And he likes to bob his head and kick his feet along with 90s music, especially the Backstreet Boys. And so this kind of went viral, and actually scientists contacted Snowball's owner and went to work with him and found that he does a pretty good job being kind of in sync with the beat, even anticipating a bit like humans do. But when they speed up or slow down the song, he pretty quickly is no longer able to do it. So it seems like it's just for a very narrow range of speeds that he can synchronize with. Whereas again, that would be really basic for us to do. So, beat extraction, another thing animals have a lot of trouble with. So with these kinds of basic ideas in place, I'm going to argue that music seems to be uniquely human. But what sorts of musical abilities are kind of baked into us? What can we do when we're born? And this whole question is something we ask about a lot of areas of cognition and brain development, but it's especially hard when we're looking at hearing, because the onset of hearing is actually during the second trimester of pregnancy. So by the time a baby is born, they have several weeks of experience with sound, mostly kind of their mother's voice and the voices around her, as well as music. So it's hard to know if they can do something at birth or right after birth, whether it's sort of innate or whether it's something they've learned over several weeks already, which is still pretty fast, but it's sort of a different thing. So with that sort of huge disclaimer, we can ask a lot of questions though about how soon certain abilities appear and the kind of the order that they happen in. So I'll use the same sort of two examples that we talked about in animals, and by 2 to 3 days after birth, newborns are able to extract a beat. So that's, again, a pretty complicated thing to do, and the way that they have assessed this is by playing music to few-day-old newborns, and sort of normal music where there tends to be notes on the important beats, they just listen to, just normal. But then if you play them a version of the music where sometimes an important beat doesn't have a note on it, it's kind of hard to explain. But basically, if there should be a big arrival note and it doesn't happen, the newborns notice, and we see in their brains a big sort of surprisal response. So they're sensitive to the idea that there should be a regular beat, and important beats should have notes on them, and they notice when that doesn't happen. And then also within the first year of life, usually around 8 months, infants are able to use relative pitch as a sort of cue for melody recognition, much like adults. So if we play them sort of 2 melodies but shifted up in pitch, they treat those as exactly the same. If you play them over and over, they kind of get bored because it's the same melody over and over. So they think of them as the same. But if you do something like change the order of the notes, which we would obviously say that's a different melody, they also treat that as different and sort of surprising because it's not the same. So within the first year, newborns are able to do some things that animals find quite challenging. So this is, of course, only 2 examples, but in a lot of cases, our sort of balance between nature and nurture is still pretty unsettled. So this is a huge area of research and really sort of fascinating. But another way that we can try to see what is sort of biologically determined and what is determined by experience or culture is by looking at different cultures around the world and seeing what their music is like and what their music perception is like. So it's been kind of hard to get this sort of data, but recently some scientists have tried to answer the question of how universal is music. We say this, and it's kind of nice to say, but are there certain features of music that are present in every culture? And so with a huge set of recordings from all over the world, some scientists did some data analysis and basically arrived at the idea that there's no one feature that they and a bunch of music theorists and ethnomusicologists can find that is present in every single culture, which is pretty interesting. There are, however, dozens of what they call statistical regularities. So certain features that are present in kind of almost all cultures, but maybe with a few exceptions. And so there seems to be some similarities. And these statistical regularities tend to be things like the idea that melodies are made up of discrete pitches that kind of hold their pitch, that the scales have unequal interval sizes, a lot of sort of music theory things. The idea that there's a regular pulse, as well as the idea, a lot of cultural things, like the fact that people tend to get together in groups and dance, and the fact that music is used in a lot of rituals, the presence of lullabies, a lot of really similar uses of music. So okay, that's kind of about the existing musical systems that cultures have, but we can also ask questions about how similar people's music perception is. So are we all sort of perceiving the same thing when we're listening to music? And one question that we've had that kind of is this whole biology versus culture thing is the case of what's called consonance. So the way consonance works is, again, pretty complicated, but consonant notes together sound good. So that's a consonant interval. Whereas the opposite, dissonant intervals, sound less good. So it sounds kind of crunchy, or like there's some tension that needs to be resolved. And this balance between, and trade-off between consonance and dissonance plays a huge part in our Western classical music. And for a long time, scientists, all the way back to the ancient Greeks, have thought that our sort of preference for consonance over dissonance is caused by like the physics of sound, or by the sort of biological way that our auditory system is set up. Whereas a lot of sort of ethnomusicologists and composers have argued that that consonance is an invention of Western music, and it's not necessarily something that everyone treats in the same way. So to try to get at this question, actually my professor and a few of my lab mates have spent the last few summers going down to deep in the Amazon rainforest in Bolivia and working with a tribe of people called the Chimane, who live a pretty traditional life. They don't have electricity or running water, and importantly, no radios or exposure to Western music. So they're pretty isolated, and they go down and they play them some sounds like this, consonant and dissonant sounds, ask them how much they like them, and surprisingly, despite the fact that they can tell the difference, they can sort of discriminate consonant versus dissonance, they don't show any sort of preference for consonants over dissonance. And this is actually pretty surprising in sort of the music perception world, that something so basic that is like fundamental to our music actually seems to be treated very differently in different cultures. And interestingly, when they repeat the experiment in bigger cities in Bolivia, they find an intermediate result, and then when they get to sort of Americans, we show a big sort of preference. So our preference for consonants seems to be an effect of our exposure to Western music. All right. So as usual, there's no real definite answer when it comes to the whole nature versus nurture idea in music. Humans definitely seem to have some basic aptitude that other species might not have. And recently we've kind of seen some increase in the complexity of whether certain things that we've assumed are sort of biological and baked in are actually an effect of culture. So now let's turn to the brain and see whether we might be able to find a region of the brain that is specifically involved in music, and maybe that can tell us something about the role that music plays in our lives. So this is, again, a tricky question because music and music perception are complex. There's a lot involved, a lot going on. And music perception involves pretty much the whole brain. So when you're hearing music, we see activity in brain regions involved, yes, in hearing sound and hearing music, but also in motor areas where maybe you're kind of getting ready to dance, or at least you're extracting a beat of some kind, in emotion areas, memory and prediction and creativity, visual imagery, maybe the music makes you think of something. So we see a lot of brain activity, and that makes it hard to figure out whether, if we see activity in a brain region, whether that activity is specific to music or whether it's sort of a byproduct of music in sort of some other way. All right, so when we're looking at whether music kind of is its own thing in the brain, we tend to use a lot of history in kind of the neurological world. So there's a long history of neurology research concerning patients who have specific deficits in language, called aphasia, as a result of injury or stroke. And interestingly, those people have sort of intact music. And relatively recently, it's gained in awareness, and the diagnosis rate has gone up. But there's also kind of the opposite sort of disorder called amusia, where people have a deficit in their music perception, but intact language and sort of everything else. So this sort of hints at the idea that music is a thing in the brain, and if you get brain damage to this certain area, you can knock out just music while sparing everything else. Or at least that's kind of the assumption that we make when we see this kind of neurological patient. So the idea seems simple. If we can do some sort of neuroimaging experiments, we don't need to rely on brain damage, we can look in normal brains, and we should be able to find this region of the brain that is responsible for music and maybe nothing else. But this has actually been surprisingly difficult for people in my field who use fMRI, functional magnetic resonance imaging, to find. And the reason for this is a lot of sort of method-y gobbledygook that I can talk about during lunch if you're interested. But the general idea is that when you do an MRI experiment, you have the sort of task that you're interested in. So you have someone listening to music, you see activity all over their brain, and then you have sort of a baseline task where they're doing something else. And you subtract the brain activity in those two conditions, and you assume that if you've done a good job, the activity that remains is due to the thing you're interested in. And a lot of early experiments use sort of silence as their experimental, or their baseline condition. But then the areas that you get back aren't specific to music, maybe it's just sound in general. So there's been a lot of sort of disagreement, and people have chosen different sort of comparison conditions. So maybe you have them listen to speech, and you subtract the two, and is that music specific? Maybe not. There's a lot of differences between music and speech. Maybe music minus scrambled music. There's not a real clear way to isolate music, so there's a lot of disagreement in the best way to do this. But really fascinatingly, and kind of the reason I came here for grad school, is that in my lab, some really smart math geniuses have been able to come up with sort of computational techniques that can bypass this whole process of having to choose your experimental and baseline conditions. Instead, just throwing a lot of data into this algorithm, and it can kind of unmix and tell you sort of the parts of the brain that are active and what they're responding to. Again, I'm happy to talk about the math during lunch if that's what you would like to do during your lunchtime. But the basic gist is that they've been able to uncover sort of a set of regions of the brain that seem to respond to music. So that's the dark blue and light blue are instrumental and vocal music, respectively. And they respond to this music more than any other kind of sound. So speech, both English and foreign speech, animal vocalizations, machinery, nature sounds, a bunch of different kinds of sounds, actually almost 200 sounds. And using this sort of algorithm, we've been able to pull out this set of brain regions that we can say are selective for music. So there's still a lot to learn about this. This is relatively new, and it involves a lot of sort of math to get there. So there's a lot of questions about, is this real, or is this just, a computational artifact? Actually, relatively recently, the same person from my lab who came up with this algorithm has been able to do experiments where he puts electrodes actually on the surface of people's brains when they're in the hospital waiting for brain surgery. Basically, they already have those electrodes there for medical reasons, and if they're willing to, they will participate in your experiment, and you can get really high quality data, the best sort of human data. And he's found sort of that these areas that he found in MRI, when you have actual electrodes there, they seem to be music selective. So we think this is real, which is very exciting, because then people like me, who maybe don't have as strong math skills, can come in and use those tools and ask the questions that I'm more interested in. Like, what aspect of music is driving these regions? Is it something acoustic? Is it melody? Is it rhythm? Is it both? Is it just whatever the person considers to be music? It's a wide open sort of space. And I'm also interested in whether this sort of music region is the same in everyone. Is this part of just being human? Or is it something that we see in our sort of Western participants who are sort of surrounded by music all the time? If I was able to take an MRI scanner to the Chimane in Bolivia, would we see the same sort of brain regions, or in babies? And there's a lot of methods problems with those questions, but these are the sorts of things that I'm looking at right now in my PhD. Okay, so, yeah, we've been looking at sort of the nature versus nurture, biology versus culture idea in music. I've argued, although feel free to debate with me, that music seems to be uniquely human. And that newborn humans have a lot of pretty complex musical abilities that they acquire within the first year. We're still learning a lot about kind of exactly when that comes about, whether it's something about the biology of our brain, or whether it's something that we learn using, our amazing brains, the way that we learn language. Maybe it's that the same way that we're learning music. We have found that music exists in every culture around the world, and that there's a lot of similarity. There's no sort of one thing that every musical culture has, but overall we tend to have some pretty basic features that are common all around the world. However, as I said with our case of consonants, there's still a lot of questions about what that really means for our music perception. Is the fact that these similarities exist, does that mean that we sort of treat them the same in our brains? That remains to be seen. When we look in the brain, we have evidence from amusia patients that music seems to be a thing that can be selectively damaged by a stroke, and leaving language and math and other things that people have hypothesized are related to music, leaving those intact and just damaging music. In neuroimaging research, there's been a long history of sort of back and forth trying to figure out whether we have this sort of music selective region. But recent sort of computational techniques have been able to pull out a set of regions that actually do seem to respond to music and not very much to anything else. And now you are right at the cutting edge of the sort of debate, and there's a lot of people who are starting to learn more about what those regions are doing and how music is sort of processed in our brains. So thank you very much to the DayCon organizers, and yeah, if there are questions, I can take those or not.
Swap while you into some questions.